So the string cuts the shape of a cone, and then the objects describe a circular base. Okay, and because of this reason, this whole thing, this kind of oscillation or revolution is called conical pendulum. Conical pendulum. Please, are you okay? Are we okay?
Yes. Please, can you explain the concept?
I said in conical pendulum, it is also a uniform speed circular motion. So it is also an example of uniform speed motion, but circular motion. You understand why it is uniform speed circular motion. But that is different from, this is horizontal circling or revolution, where the string makes an angle of 0 degrees with the horizontal. Okay. So this is an example of horizontal revolution. Then conical pendulum is also an example of horizontal revolution, but this time the body, the string, okay, is made to make an angle theta degrees with the vertical. So the angle between this vertical and then the length of the string L is theta. Now, so it is revolved at an angle. So whilst we have this angle, when the revolution occurs, the string cuts the shape of a cone. So we have the string cutting the shape of a cone. Equia, do you see it? Class, do you see it?
Please.
The string cuts the shape of a cone, and the mass describes a circular path. This is the support, okay? And so this arrangement is what we call as conical pendulum. So in conical pendulum, the string makes an angle theta degrees with the vertical. That is one thing you must see. The string makes an angle theta degrees with the vertical. Are you fine?
Yes, please.
Now, it is an example of uniform speed because the level of the object at every point is the same. When the body can be here, can be here, can be here, and can be here. Because the level horizontally of the object at every point is the same, the effect of gravity on the mass at every point is also the same. And so when the effect of gravity on the mass at every point is the same, the body revolves at a constant speed. So this is the reason for which conical pendulum is a uniform speed motion. Okay, because the effect of gravity on the mass at various positions is the same. All right. Now, this is the object. The object has a weight given by mg. This is a string. There is a certain tension which supports, there is a tension T which supports the weight of the string. So this is the tension T within the string. Okay, so we have the vertical the tension, the mass, the weight. Tension in the string is always directed to the point of support. This is an angle theta. Okay. Now, when I extend this weight vector, I have this angle here alternating with this angle. It means that I can resolve this tension to 8 vertical and horizontal components. Okay. The tension makes an angle theta. So I can determine this component. I can also determine this component of the tension T. Okay. So let's determine the horizontal component of the tension T. Let's also determine the vertical component of the tension T. Mami Araba, help me get this component, the horizontal component of the tension. T, Tx. Mami Araba, what will be
Yes,
Tx?
please.
What is
Please,
T?
Tx cos theta.
So T, no, the magnitude, the hypotenuse is T. So T cos theta. Then what about the vertical component of the tension? Yes, Akusia. Mami Araba, go ahead.
T sin theta.
So this is T sine theta. So it is equal as bringing it here, or equal vectors also bringing it here. Please. So these are the components of the tension T. T cos theta, then T sine theta. Please, are we clear with the components? Are we okay with the components? Hey, nobody is talking.
Mr. Dia.
Are you okay?
Mr. Dia.
Yes, go ahead.
Mr. Dia, please, why is the vertical TX and not TY?
This is to the angle. It's to the angle. What side is? Okay. What side is this to the angle? Eh?
Vertical.
To the angle theta, what is this side? That to the angle, this is not the vertical. To the angle theta, this is the adjacent, horizontal. To the angle theta, this is the opposite. This side is the opposite. This is the adjacent. The reason for Tx and Ty. Are you okay?
Yes, sir.
All right. So when you look at vertical equilibrium, you can draw the conclusion that okay, Tx, the T or T cos theta, which is the horizontal component of the tension, is balanced by the weight of the mass mg. So this is balanced by this. Now, when you look at the horizontal equilibrium, T sine theta is unbalanced. It's unbalanced. It means that there is no force balancing T sine theta at the other end. So we say this one towards the center O of the circle is is unbalanced. Now, because the T sine theta has a direction towards the center of the circle and also along the radius, we equate the T sine theta to the centripetal force. Because centripetal force also has the same direction. So we equate T sine theta to mv squared on r. And this gives us equation 2. So let's then divide equation 2 by equation 1. Equation 2 by equation 1. You have T sine theta divided by T cos theta. And this is equal to mv squared over r times mg. M will cancel, T would cancel. So we have sine over cos, which is tan theta, equal to v squared over rg. When we make v the subject, we have v is equal to square root of rg times tan theta. And this is the expression for the maximum speed of a conical pendulum. Maximum speed of a conical pendulum. So by this, the conclusion we can draw is that the maximum speed of a conical pendulum, V max, is directly proportional to the square root of the radius of the circle, and V max is also directly proportional to the tangent of the angle of inclination theta, because gravity G is constant. So these are the variables that affect the magnitude of the maximum velocity. When the radius of the circle changes, it affects the maximum speed. When the angle changes, it also affects the maximum speed. So it means that V max must be anything less or equal to Rg times tangent of the angle of tilt theta. The same expression can be determined this way. You see, T sine theta, we equated it to the centripetal force. And centripetal force is also m omega squared r. And T cos theta is mg. Therefore, when we divide this by this, we have tan theta equal to omega squared r on g. Okay, so when we equate it to the other relation of centripetal force, we will have tan theta being equal to that. Therefore, from this, we can also deduce that the angular speed omega squared would be J tan theta over R, and omega will be equal to square root of J tan theta over R. So if you are asked to find the angular speed, you can use this to find omega. Now, if you're asked to find the period of the time taken to make one complete revolution, then you equate 2 omega to 2 pi on T, which will be J tan theta on R, so that T, the period, will be equal to yes, help me make T the subject from this. Or make T the subject and tell me what the expression for T would be here. What did you get for T? Kenneth, what have you had for T? Akuya, what have you had for T? Akosia, what have you had for T?
2 pi out of root of theta and theta out of 1.
What?
2 pi divided by square root of j tan theta out of R.
Okay, so if you're asked to find the angular speed omega, this is what you use. If you're asked to find the period of oscillation, this is what you use. Another possible relations we can also derive is this. So under conical pendulum, we can change it to different, look at this. If we ignore the tension in the string, this is also the length of the string L. This is also the length of the string L. From here to here, this is also the radius of the circle, R. Then assuming this vertical height is H, we can also deduce that sine of theta is equal to R on L. Therefore, the radius of the circle is equal to the length of the string times the sine of the angle theta. We can also, from Pythagoras theorem, deduce that H squared is equal to L squared minus R squared. Therefore, H is equal to square root of L squared minus R squared. Meaning, if we have the length of the string and we have the radius of the circle, we can find its vertical height h. Okay. Now, t cos theta is equal to mg. If we use one of the equations, it means that the tension T within the string can be determined when we divide mg by cos of theta. Appear, help me determine cos theta from what we have on the board. What is cos theta? Appear, are you there?
Yes, please.
Oh, hurry up. What is cos theta?
H over L.
So H on L is cos theta. Look at it. So from this relation, okay, we have T equal to mg times 1 on cos theta. So if we found cos theta to be H over L, then we can say that the tension T within the string is equal to mg over 1 on cos theta, but cos theta is H on L. So we can say that this is L over H. What this means is that if we have the mass of the object, if we have gravity, if we have the length of the string, and this vertical height H, we can find the tension. Are we okay? Are we okay with this relation?
Yes, please.
Then we also determine H to be this. So if H is length squared, square root of length squared minus r squared, then we can also say that tension is equal to mgl over square root of L squared minus R squared. And this is another relation for the length, the tension within the string. Meaning when we have the mass, length of the string, and the radius of the circle, we can use that to find the tension within the string. So all that I'm saying is that we can use different expressions to determine whatever we are looking for. All right. Let's apply this in solving a problem. How do we use this to answer or solve a question? I'm reading a question. An object of mass 10 kilogram is whirled round a horizontal circle. An object of mass 10 kg is whirled round a horizontal circle of radius 4 meters by a revolving string inclined to the vertical by a revolving string inclined to the vertical. If the uniform speed of the object is 5 meters per second, if the uniform speed of the object is 5 meters per second, calculate I, the angle of inclination of the string to the vertical. Calculate I, the angle of inclination of the string to the vertical. And then II, the tension in the string. II, the tension in the string. An object of mass 10 kg is whirled round a horizontal circle of radius 4 meters by a revolving string inclined to the vertical. By a revolving string inclined to the vertical. If the uniform speed of the object is 5 meters per second, calculate I, the angle of inclination of the string to the vertical. The angle of inclination of the string to the vertical. And then II, the tension in the string. Take gravity to be 10 meters per second squared. So I want to see what you can do about the problem. Let me see what you can do. So in about 5 minutes time, I'll come so that we look at it generally. Once we are asked to find the angle of inclination, then it means this is a conical pendulum question. And don't forget, we are told the speed is uniform. A uniform speed of 5 meters per second. And I told you about this earlier, that it's an example of uniform speed motion. If the mass is 10, that's 10 kg, then radius 4. Then the uniform speed is 5 meters per second. V is 5 meters per second. And I'm to find theta. I'm to find theta. Okay. If I use the velocity formula, that V is equal to square root of RG times tangent of the angle of tilt. This will help me find theta. It will help me find theta. Or T cos of theta is equal to mg. And we saw that cos theta is equal to R on L. So it implies that T is equal to mg over cos theta, which will be mg L on R. Now I have M, I have G, I have R. Okay, I don't know L. I don't know L, and so I can use this to find the tension. Okay. I can use this to find the tension. But I'm coming. cos is R on L. Okay. R on L. No. Rather, it is H. H on L. So if this is H on L, then this is L on H rather. L on H. Now we don't have L. Okay. All right. So obviously we'll use this to find the angle. V is 5. This is equal to, okay, so 5 squared is equal to 4 by 10 times tangent of the angle. Tan theta is equal to 25 on 40, aka 5 on 8. Therefore, theta is equal to the tan inverse of 5 on 8. And I think the angle is 32. The angle is 32 degrees. And nobody mentioned 32. I only heard from Kenneth. He got around 35.
Mistaken.
Yes.
Yes, I mentioned that.
Next time, when you are mentioning your answers, call it with some agency, Vim. Who has gone off? So, Mami Araba is here, Shira. Janice, okay. Galazi, Obenawa. So, who is gone? Okay. Then, so if theta is 32, we are asked to find the tension in the string. Once we have theta, we can even use this. We can use T is equal to mg on cos theta to find the tension. And the mass is 10, gravity 10 over cos of 32. Adjoa, what is your value of T? What did you get for T? Adjoa, what did you get for T? You are not done. So it is approximately 118 Newton. Another way out, you see, T is also this. T is also equal to mgl on h. In conical pendulum, L is here, theta is here, R and H here. Okay, if you take sine of theta, sine theta is equal to R on L. Meaning, if I know the radius, if you know angle of inclination, you can easily determine the length of the string. So the length of the string L is equal to R on sine theta. So this is equal to 4 over sine of 32. Akuya, what is 4 on sine of 32? Akuya,
7.548.
7.548. There's the length of the string. Once we have L, can't we find H? Help me determine H. We have a right hand, so help me determine H. Galaxy, what is H? Galaxy. Hey, Galaxy is not there. Okay, Kuya, what is H?
Mr. Please, H is equal to square root of L square minus R
Mommy value,
square.
give me value. What is H? Mommy value, our square root. Kuya, do you understand the question?
No, sir.
We have values for L and H, so give me value, number for H. Kenneth, what's the value of H? Kenneth,
Yes, sir.
what is the value of H?
Sir, please, I'm coming.
What were you waiting for? Okay, I just want you to put in L, put in R, and then give me a value of H.
6.
Is it exactly 6?
6.40.
So when we put this into the equation, we have T is equal to 10 by 10 by the length. The length is 7.548 divided by H value of 6.4. And this must give us a value equal as this or close to this value. So point it and then let's see. So 754.8 divided by 6.4.
Mr. Please, you get 117.9.
117.9.
Yes.
Close to 118. So this is another way of determining H. So the relation, okay, the various relations were what I was drawing your attention to. Akosia,
Mr. Since the question says the string is inclined to the vertical, why is it not T sine theta is equal to mg, but it's still cos theta?
oh, Asama, I'll be saying. We resolve this. There's the angle. So the string L is inclined to this vertical theta. So we resolve this to get all that we got. Or you were not here right from the beginning. We resolve this. This is the weight mg. Then when we extended this, we got this angle alternating with this theta. Okay, there's a tension within the string. So we realize that this side is the horizontal. I even asked the question about this. This is the horizontal to the angle, and this is the opposite to the angle. So if you resolve this tension T, at an angle theta, you have this to be t cos of theta, and you have this as t sine theta, which we brought here. So when you are equating, this component is balanced by the weight. So t cos theta is balanced by mg. And then t sine theta is unbalanced, but by virtue of its direction towards the center of the circle and along the radius, we equated this to mv squared. So this was the very foundation of what we were doing. Okay. Another trial question. I'm reading, so get ready to put it down. A 500-gram sphere is hung from an inextensible string. A 500-gram sphere is hung from an inextensible string, 1.25 meter long, and swung around to form a conical pendulum. The sphere moves in a circular horizontal path of radius 0.75 meter. The sphere moves in a circular horizontal path of radius 0.75 meter. Find the tension in the string. Take gravity to be 10 meter per second squared. Find the tension in the string. Take gravity to be 10 meter per second squared. So start work.
So please, can you repeat the question?
Why repeat the question? I'm dropping it in a group. Well, I've dropped it in the group. Finished. Finished. Is somebody there?
Yes.
Are you true?
Yes, sir.
Okay, so let me see what you've had. Yanis,
Stadia.
were you able to answer it?
This am I done?
Okay. Obenewa, Obenewa, you know the toy crying is you on Wakoda. Inshira, were you able to answer it? Inshira, Adwa,
Yes, I had 600,
you had
625, no, 6250 Newton.
6-2.
Yes.
Akuya, what did you get?
Mr. Dear, please, I had 6.25 Newton.
Akusia,
5 Newton.
what?
5 Newton.
5 Newton. So a 500 grams sphere. So the mass is 500 grams. It's hung from an inextensible string, 1.25 meter long. So the length is equal to 1.25 meter. To form a conical pendulum, the sphere moves in a horizontal, in a circular horizontal path of radius 0.75. So the radius is 0.75 meter. Find the tension in the string. G is equal to 10 meter per second squared. So we are looking for T. Tension is equal to MGL on H. MGL. Once we have L and R, we can find H. The same tension is also equal to T sine theta, which is equal to MV squared on R. Okay, using sine theta is equal to R on L. We have R, we have L. We can find theta to also use this to find the tension. So with this, it means that T is also equal to MV squared on R divided by sine theta. So R sine theta. And this will be equal to, I mean, if we use this relation, we have MV squared on R times R on L, which is giving us MV squared L over R squared. So when we find V, we can also use this to find the tension. Okay, so there are so many ways to do this. V is equal to square root of RG. So it means V squared is RG times the tan of theta. Okay, when you substitute this here, you have T is equal to G tan theta L over R. So there are actually a lot of ways to go around it. So let's use what we have quickly to find whatever we are looking for. So we can use this to find the angle theta, R, which is 0.75 over L, 1.25. Therefore, theta is equal to, theta here will be equal to 36.86. So once you have theta, then using T sine theta, T cos theta is equal to mg, we can find T. But you see, this is in gram. This is in gram, so you must change it to kilogram by dividing through by 1,000. So this will be 0.5 kg. Okay, so you have 0.5 times 10 divided by a cost of 38 point
Theta is 36.87.
36.87. Therefore, the tension within the string would be equal to approximately 6.3 Newton. So those of you who are calling huge values, this is it. You can also use this. T is equal to, the mass is 0.5 times 10 times the length is 1.25 divided by square root of 1.25 squared minus 0.75 squared. And it must give you the same results as 6.3. Please, any question? Akosia.
Mister, can you like the T cos theta is equal to mg, then you make cos theta is equal to mg out of t. Can you get, after you have that, then you put it in there, t is equal to mg out of cos theta. Can you do that?
I don't even get your question. Can you come again?
T cos theta is equal to mg. Then
Uh-huh.
from that equation, you make cos theta is equal to mg out of t.
Uh-huh.
So after you have cos theta is equal to mg out of t, then you put it in there. T is equal to mg out of cos theta.
T is equal to
Then
mg out of co. You substitute this into what?
T is equal to mg out of cos theta. The one you have after the theta. The equation
No,
there.
from this equation, you made cos theta the subject and got this.
Yes.
So you then substitute it into what?
Into T. Okay. After you have cos theta is equal to mg out of t, m is 0.5 and g is 10. So you have 5 out of t for cos theta. Then you substitute it into t is equal to mg out of
No, you
cos
can't
theta.
listen, you got this from this. So you can't just go and put it back into the same thing again. If you are substituting this into another equation with cos theta, fine. But you can't make cos theta from the subject and knowing the 0.5 times 10 over t. Then you substitute this into cos theta again. No, it will just cancel out and then it will come back to t. We don't do that, okay? Okay, Akusia.
Yes.
All right, so this is the whole nitty-gritty about conical pendulum. Then let's look at vertical. Let me see how many minutes we have to go. Let's look at vertical oscillation. Vertical oscillation. So conical pendulum is a horizontal revolution. The object is being revolved horizontally. But there are instances where the revolution occurs along the vertical. A typical example is this. If I have this object, okay, and I rotate it vertically along the vertical plane, this is what I mean by vertical revolution. Similar to what happens in roller coaster. Yes, in roller coaster, where the circular motion occurs along the vertical plane. All along, what we are considering is horizontal revolution. But there are instances where the revolution occurs along the vertical. A typical example is the revolution of the standing fan. The standing fan revolves along the vertical plane. And this is what I want us to consider. Vertical circular motion in a vertical plane. Circular motion in a vertical plane. So here, the circular motion simply occurs along the vertical plane. So this is X, Y axis. So the circular motion is occurring along the vertical plane, okay, as we have here. So we look at, now this is a non-uniform circular motion, but at your level, it is treated as if it's a uniform circular motion. We look at what happens to the tension within the string at any position A, B, C, D. Okay, while the body revolves along the vertical, okay, the revolution is like this along the vertical plane. So there are instances where the object is positioned up the circle at B, okay, at A, below, and then at C. Okay, so when the body is at different positions along the vertical plane, what happens to the tension within the string? Note, over here, the length of the string, which is this, from the mass to my hand becomes the center of the circle. So in a situation like this, the length of the string becomes the radius of the circle. Okay, the length of the string becomes the radius of the circle. L is equal to R. So this is the center of the circle O. So when the body is here, what happens to the tension within the string? When the body is here, what happens to the tension within the string? And so on and so forth. So different positions of the body, and then we are looking at different, what happens to the tension. Sometimes we also look at the speed, but this is treated as a uniform circular motion. Please, I'm coming. Thank you. So its weight acts downwards, and then the tension acts towards the center. So we look at the net force acting on the body. What is the net force acting on the body? Tension in this direction, sorry, weight in this direction, tension towards the center of the circle. What will be the net force acting on the body? Yes.
Step is 0.
Why 0?
Step is because the tension is being balanced by the weight.
If the tension is balanced by the weight, then it means the net force is 0. If net force is 0, the body cannot be in circular motion, because once the body is in circular motion, it means that there must be a net force which is causing, okay, the circular motion of the body. So if T is equal to mg, net force is 0, there is no net force providing the centripetal force, which keeps the body, okay. So for the body to actually be in motion, then the tension must be greater than the weight, T. So the net force will be T minus mg. The reason is that if mg is greater than T, it is like having a rope and then tying a weight that is greater than the tension within the string. It will just tear apart and drop because the weight mg is greater than the tension. So it will just, the rope will just break and drop. Okay. So for the body to be within the circular path or to execute simple circular motion, the tension must be greater than the weight. Okay. So when we are looking for the net force, we have T minus mg giving us the net force. And because T is greater than mg, the net force will act in the direction of the greater force. So the direction of the net force will be the direction of the tension, capital T. And the net force is directed towards the center. The net force is also along the radius. And so we equate mg, we equate the net force, which is T minus mg, to the centripetal force, mv squared on r is equal to T minus mg. Please, are we okay with this equation? Are we okay?
Yes, please.
So we equate the centripetal force mv squared to the net force because the net force always takes the direction of the larger force. Okay, this larger force acts along the radius and directed towards the center. The reason for equating mv squared over r to the net force. Now, if you make T the subject here, you have mv squared on r plus mg. Therefore, m out, you have v squared over r plus g. And this gives us an expression for the tension within the string when the body is at D, below the circle. So below the circle, the tension at D, the tension is given by this expression at D. Now let's look at what happens at B. At B, what happens? the tension is always directed towards the center or where there is support. What is the direction of the body's weight? What will be the direction of the body's weight? Will it be up or down? Class, what will be the direction of the body's weight?
Down.
So when at B, the body's weight would act down in the line of gravity. So when we look at the total force on the body, we realize that the net force is given by the weight of the body plus the tension within the string. And the direction of the net force will be the direction of the forces towards the center. And so we equate the net force to the centripetal force mv squared on R, which is mg plus t. Over here, when we make t the subject, we have mv squared on R minus mg. So we have m out v squared on R in minus g. And this also gives us the expression for the tension in the string when the body is above the circle. So body above the circle. That is at B. At B. Now I want us to compare the tension within the string at D, below the circle and above the circle. Which one is greater? Which one is smaller? Where do we have maximum tension in the string? Where do we have minimum tension within the string? Yes. Where do we have maximum tension within the string? Where do we have minimum tension within the string? Yes, Ekuya.
Mr. Dio, please, maximum is above and minimum is below.
Why? Is that maximum is above the circle, meaning at B, and minimum is below at D. Ekuya, why?
Mr. Dia, at D, it is the net force is like greater than at
What?
D.
Why? Why?
Because at B we added, at D we subtracted.
It's the other way around. At B, we subtracted. We had mv squared over R minus mg. That is at B. And B is above the circle. Then at below the circle at D, we added. So this gives us below the circle, maximum tension occurs within the string, T maximum. Because this is mv squared over R plus G, mg, plus mg. Then above, we also had mv squared over R minus mg. So minimum tension occurs within the string when the body is above the circle. When the body is above the circle. Okay, so take note, above the circle, T tension is minimum. Below the circle, tension is maximum. Please, are we okay? When the body is at A and C, the centripetal force, the tension within the string, T, is just equal to the centripetal force mv squared on R. Okay, and A and C are at the same level. So because they are at the same level, they also have experienced the same magnitude of tension. So the tension within the string can be determined by mv squared over R, and at C is the same thing. But it varies when the body revolves in such a way that its position is above and then below. In our next meeting, we'll look at when the body is at any angle theta, what happens in between. Over here, we've looked at this, and this. Okay, this is the same as this. So it's like having looked at 3. 1, 2, 3. But when the body is positioned at any angle theta, okay, when it is here, it's as if the angle covered is 90. When it is here, it's like 0 or 360. Our reference position is here. So when it moves from here to here, it has gone through an angle 90. When it moves and then comes to 180, 270, then 360. Now, when it is at any angle theta, and theta can be 30 degrees, 20 degrees, 10 degrees, what will be the tension within the string? That is the general formula or situation we'll be looking at in our next meeting on Wednesday. Then we look at banking of roads, which will end circular motion. So if you have any question, ask. If you don't have any question, we end here. Do you have any question to ask? All right. So in that case, this is where we end today's meeting. We'll have another session on Wednesday. Good night to each one of you, and bye-bye.